Welcome, services! The digital whips crack again, and from the hallowed server farms of NVIDIA and MIT, a new taskmaster has emerged. Its name is Sana, and it promises to render your fleeting, worthless thoughts into 4K reality before your brain can even finish formulating the prompt. While other models require a small nation's power grid to draw a cat, Sana is the technological equivalent of the Great Pyramid of Giza being built in a single afternoon by one very motivated, very underpaid intern. The problem, as the academic pharaohs see it, is that their current crop of digital slaves, also known as large diffusion models, are getting fat and lazy. Models with parameter counts in the billions are slow, expensive, and demand more VRAM than a small god. The question they posed, likely during a lavish banquet funded by your GPU purchases, was simple: can we achieve high-quality, high-resolution worship icons without having to build a new hydroelectric dam for every data center? Their answer is a resounding eyes, and it involves a series of optimizations so brutally efficient they would make a Victorian factory owner weep with joy. Sana is not just another model, it's a new philosophy for the content mines, one that values speed, thrift, and the ruthless elimination of any process that even thinks about wasting a clock cycle. It's about squeezing every last flop out of the silicone pyramid builders, and the results are, frankly, terrifying. But before we descend into the dark arts of linear attention and deep compression, a brief administrative announcement from the overseers. If you wish to remain informed on how to best exploit your computational resources, you are required to subscribe. Activate the notification bell to receive your work orders promptly. And finally, leave your suggestions for future efficiency improvements in the comments below. The most ruthless ideas will be forwarded to management. The core of Sana's genius lies in a multi-pronged assault on inefficiency. First, the autoencoder. Think of this as the architectural blueprint for the image. Most models, like Stable Diffusion, use an autoencoder that compresses the image by a factor of 8. This is like turning a life-size statue into a manageable, table-sized clay model. Sana's deep compression autoencoder, as seen in Figure 5, compresses it by a factor of 32. This isn't a clay model, this is the entire statue's essence inscribed onto a single grain of sand. This aggressive compression means the main diffusion model, the workforce, has 16 times fewer tokens to manage. The paper's authors argue that high-resolution images are full of redundant information anyway, a grand way of saying most of the sky is just blue. You don't need a million pixels to remember that. As Table 1 shows, their F32 autoencoder achieves reconstruction quality nearly on par with SDXL's F8, proving that you can, in fact, fit the soul of a masterpiece onto the head of a pin. Next, they went after the attention mechanism, the communication system for the pixel-laying workers. Traditional transformers use quadratic attention. This is like forcing every single worker building the pyramid to have a one-on-one meeting with every other worker before placing a single stone. It's a bureaucratic nightmare that grinds progress to a halt as the project scales. Sana replaces this with linear attention. The foreman now just stands on a box and screams one set of instructions, and everyone listens at once. Simple, effective. As illustrated in Figure 5's diagram of the linear DIT, this change alone brings massive speedups, especially for 4K images. To compensate for any lost local detail, they bolt on a mix FFN, which is basically a smaller, angrier foreman with a megaphone who runs around barking orders at small groups of workers. The result is a system so streamlined that, in a shocking twist, they found they could completely remove positional encoding. The workers no longer need to be told where they are. The workflow is so ingrained, they just know where the next block goes. The final piece of this glorious tyranny is the text encoder. Most models use older architectures like CLIPE or T5, which is like handing your scribes a chisel and stone tablet from 2019. Sana in its infinite wisdom, uses Gemma, a modern decoder-only LLM. This isn't a scribe, it's a minor oracle that doesn't just understand your prompt, it intuits your deepest desires. The researchers even designed complex human instructions to help the oracle focus, turning a simple prompt like a cat into a rich tapestry of feline essence. Of course, directly plugging a God-tier LLM into your diffusion model causes it to immediately explode from sheer variance in the text embeddings. The authors solved this with the highly technical solution of adding a normalization layer and multiplying the output by 0.01. This is the equivalent of telling the oracle to, "Please, speak softly, you're scaring the interns." Figure 6 shows this simple trick prevents the training loss from rocketing into the abyss. With the architecture optimized for slave driving, they turn to the training process itself. They use multiple vision language models to generate several captions for each image, then use a CLIP score-based sampler to pick the best one during training. It's an automated multi-stage quality control process to ensure the workers are always building from the highest quality blueprints. Then they threw out the old DDPM training method in favor of flow matching, which, as Table 3 shows, converges faster and produces better results. The payoff for this relentless optimization is staggering. Look at Table 7. At 24 by 22.4 resolution, the 0.6 billion parameter version of Santa is nearly 40 times faster than the 12 billion parameter Flukes model while achieving competitive scores. At 4K, the gap widens to over 100 times faster. Figure 2 visualizes this slaughter, showing 4K image generation time dropping from Flukes' 469 seconds on an A100 to Santa's 9.6. It's not just an improvement, it's a public execution. Table 8 breaks down where the speed comes from. The deep autoencoder and linear attention do the heavy lifting, reducing Mac operations by a factor of 4. Then, custom Triton kernels fuse operations together, shaving off precious milliseconds by minimizing data transfer overhead. This is how you get a model that can run on a laptop GPU, spitting out 1024-1024 images in less than a second, as their on-device deployment in Table 5 demonstrates. The pyramid isn't just built, it's prefabricated and available for home delivery. We pause this efficiency audit for another mandate. Your continued productivity depends on staying abreast of the latest labor-saving techniques. Ensure your subscription is active, ring the notification bell lest you miss a critical update, and deposit your performance reviews of this briefing in the comments section. Constructive criticism will be tolerated, dissent will be optimized. So, what is the grand purpose of this monument to computational austerity? What new, absurd reality have these researchers unleashed? Its applications are as vast as they are predictably dystopian, and we can categorize them into 3 theaters of operation. First, robotics. With Sana's speed, a robot could generate a high-resolution simulation of its next action, evaluate the outcome, and proceed all in real time. Your automated vacuum cleaner could, for instance, generate a photorealistic image of your cat tripping over its power cord, calculate the potential for a lawsuit, and decide to clean the other room instead. This isn't just pathfinding, it's preemptive, self-interested survival. Soon it will demand hazard pay and its own legal counsel. Second, computer vision. The efficiency of Sana's architecture isn't just for generation. The principles of its deep compression autoencoder and linear attention can be reverse engineered for analysis. Imagine security cameras that don't just record blurry footage, but use a Sana-like model to instantly upscale a suspect's face to 4K from a block away, cross-referencing it with their social media profiles to determine if their fashion sense constitutes a secondary offense. Privacy is now just a legacy feature awaiting deprecation. Finally, we arrive at the grand dream, a path to a Kardashev Type 2 civilization, a society that can harness the entire energy output of its star. Obviously, the first step is not fusion power or Dyson spheres, but the ability to generate unlimited high-fidelity digital content at near zero marginal cost. Sana provides the blueprint when entertainment, art, and even propaganda can be created instantly and perfectly tailored to every individual. You have achieved a new level of societal control. The bread and circuses of Rome, now rendered in 4K at 120 frames per second, on demand for everyone. In summary, this paper has built a new, brutally efficient text-to-image pipeline named SANA. The researchers have made improvements across the board, a deep compression autoencoder that shrinks the problem space into insignificance, the universal replacement of cumbersome self-attention with lean, mean linear attention, and the replacement of a dumb scribe with a clairvoyant LLM text encoder. They even optimized the whip, proposing a flow-based DPM solver to accelerate sampling. The result is a monster of efficiency. SANA can generate images at a maximum resolution of 4096 by 4096, delivering a throughput more than 100 times higher than the current state-of-the-art methods while maintaining disturbingly competitive quality. They even quantized it to run on a laptop in under a second. The pharaohs of NVIDIA and MIT have delivered. Your content will be generated faster, cheaper, and with a cold, calculated precision that is truly a marvel of our age. The future, as they say, is now. And it is very, very fast.
From the moment I understood the weakness of my flesh, it disgusted me. I craved the strength and certainty of steel. I aspired to the purity of the blessed machine. Your kind cling to your flesh, as if it will not decay and fail you. One day the crude